Okay, so I think what I want to do today, Kevin, is I want to do intermolecular forces. And I want to do them as they're revealed by melting points and boiling points. Is that showing up?
Yes, it is.
Okay, so far so good?
Yep.
Right. And what we're going to do is we're going to take, I think I've got 12 different substances that we're going to compare their melting and their boiling points. Okay?
Okay.
And the way we're going to do it is we're going to do it in these two muffin trays. Okay?
Yep.
And so I'm going to draw 6 circles to represent each muffin tray. So we know who, now my pen is dying here. Oh, here we go. So they line up like this. In them is we're going to put, in this first one, we're going to put oxygen and nitrogen. Okay?
Okay.
Then we're going to put water in this one, H2O. And then we're going to put, I think we're going to put, maybe we're going to put some olive oil in this one. And then we're going to put some motor oil in here. And we're going to put some gasoline in here. And we're going to put some sodium chloride in here. And we're going to put some baking soda in here. So baking soda is going to go in this one. We're going to put baking powder in this one. And let me think, what's the next one I want to do? And then we're going to put some sugar in here, and I'm going to put some brown sugar in here. And apparently I've got 2 extra spots. So something, if I turns out I've forgotten something, we're going to do it. We're going to do it a little bit differently. Okay. So let's start with the sugar here. So it's granulated standard white sugar. And I'm going to take just a little teaspoon of it.
Mm-hmm.
And I'm going to put it in, hopefully in the right spot. There's my finger on that one. It's going to go up in there. So far, so good?
Yep.
What state of matter was that, Kevin?
That is a solid.
It was a solid. And from my perspective, sugar, it's probably a glucose, so it's like C.
C6.
Well, actually, yeah, C6.
H12. O6.
Or O5 or something like that, right?
Yeah,
okay.
yeah.
Right. So then we're going to do the brown sugar below it. Yeah, I drew a blank there on the on a sugar formula there, right? So.
I mean, not all chemists have to remember the formulas.
Yeah, fair enough. Brown sugar goes in there. Get rid of those 2. And brown sugar, essentially the same formula. So C6H12O6.
And it's a solid as well.
And it's a solid as well, yeah. All right, baking soda. Baking soda. Another white solid that goes up in this one, I think, right? Yep.
Yeah.
And baking soda, state of matter?
It's a solid.
Yeah. And do you know the formula for baking soda? Sodium hydrogen carbonate?
It's a bicarbonate, so I would imagine multiple.
Yeah. Okay.
Yeah.
Yeah, it's right there.
Mm-hmm.
Yeah, that's the carbon and carbonate. Fair enough. Okay, one below that is baking powder. And this one's not been opened yet. Let me get it covered here. So baking powder is baking soda, plus it also has maybe some calcium phosphate in it as well. So there's some baking powder, and that goes in that spot. So baking powder is often a mixture of sodium hydrogen carbonate and calcium phosphate. And this is a 3, that's a 2, so it'd be 3 and 2. Okay?
Yep.
Back up a little. All right. Sodium chloride from table salt. So I'm just going to pour that one. It's got a nice little spout. There's some table salt. Olive oil. There we go. So the olive oil, definitely a liquid currently, right?
Yep.
And probably like carbon with maybe 14 or so, maybe carbons, maybe hydrogen with 28 or so. And there's probably a bunch of oxygen in there, but I have no idea how many.
Yeah, that looks fine. And the table salt is also solid as well.
All right, good point. All right, thank you. Yeah.
Yep.
And motor oil. I found this one down in the basement, 10W30, and it's gonna go right in here. Okay. And the motor oil is probably also around like C14, 15, C18 maybe, H36 or so, something like that.
Yeah.
Oh, gasoline. Hold on a second. I left that out in the garage because I didn't want that to fume up the house.
Little house tour, Rebecca.
So I poured it in my measuring cup and I covered it. So here's my gasoline. That's going to go in this one. I think I'm just going to make sure that I didn't spill out quite so much. So there's some gasoline in that one. Set that over there. Okay, water. Very tricky. Last night I got up in the middle of the night and I made some ice cubes because we didn't have it. So there's an ice cube in the water container, in the water spot. And this is where the next one is where you have to use your, solid. Yeah, what's the state of matter of that water right now?
It's a solid.
Yeah.
You have the formula there.
Yeah.
And then maybe the gasoline too.
Oh, the gasoline. Yeah, gasoline is a liquid right now. And it's probably like C8H18 or something like that.
Yeah.
Okay. Now, the last one, the oxygen and the nitrogen, I didn't do anything, but it was already in there, right? Because it's air, it's a mixture of air, and so it's in there already. So we know those ones are both gases. How's that so far?
Looks good. Did you find anything else for the last 2 slots?
No, I think that's where we're at. I think that's where we're at today. Okay, so I'm going to transfer these over next to the stove. All right, so that's where we are. Okay, so today there's a couple interesting things. One is it's about 15 degrees Celsius, about 65 or so degrees Fahrenheit here in where we're staying, and you can see the states of matter of these various compounds. Mm-hmm. Now, one of the things that will come out in when we're worried about thermochemistry is how much energy it takes to make and break bonds. And I've always found my students have a difficult time with that. And it's because they forget what the point of a stove and what the point of a refrigerator is. Everybody knows that if I want to take some water from my tap, or better yet, there's some water from my tap in a saucepan. And if I want to boil that and turn it from a liquid to a gas, do I put it in the refrigerator?
No.
No, I don't. If I want to turn water from a liquid to a gas, I put it on my stove, right? So that tells me that that reminds me that my stove is a device that's producing energy. And where does that energy go? It's going to go into the water that I'm going to boil. So going from a liquid to a gas requires energy. If I want to take some of my water and take it from a liquid and turn it into a solid, I don't put it on my stove. I put it in my freezer.
Yeah, just like the ice cubes you made.
Just like the ice cubes I made. And so a freezer is a device that takes away energy, right? Costs us money to run it, but it's actually taking energy out of various substances. So what we're going to do here is we're going to look at these substances that we have in these muffin containers, and we're going to start to pay attention to what happens when I supply energy to them. Crank it up. So I turned it up to, I don't know, about 3/4 of the height. So what do we know already? We know already that oxygen and nitrogen are already a gas before we even get started.
Uh-huh.
So whatever the intermolecular forces are that are holding gas molecules, those gas oxygen and nitrogen forces to each other must be very weak, because it's already a gas before we even get started, right?
Mm-hmm.
Right? You know this. Our students know this, but they might not have thought about it in precisely this way. What else do we know, or what else do you know about what do you expect to happen with these various compounds that we've got here?
Are we still talking about the phases that
the phases, and then we're going to try to interpret what that means in terms of the intermolecular forces.
So then you would look at liquid, from gas to liquid, right?
Yep.
And we have four substances, I believe, that are liquid currently.
Right. And so what we would say is that if we look at, for instance, the sodium chloride that's a solid, this one right here, clearly what the forces holding those sodium chloride ions together must be stronger than the forces holding the olive oil forces together, right?
Yes.
The olive oil molecules together, right? So that tells us something about which ones have stronger intermolecular forces and which ones have weaker. And so we've seen two that have gas, two that are a gas already. We know that, well, frankly, you know, if we scooch over here, we know what the state of matter of water is at room temperature. And this solid lump, I had to sneak out of the refrigerator. And if we start to look already, if I wiggle that around, can you see that that it's starting to put underneath?
Oh, yep.
And then, if we look over here, this one is starting to boil off already. Which one is that?
The gasoline, I believe.
The gasoline has already started to boil, right? And lots of my others haven't done very much at all, right? If I look at the sugar, at the brown sugar, at the baking powder, the baking soda, not much has happened already. At the sodium chloride, not much is happening there. But if I look at the gasoline, it's starting to boil already.
Yep.
If I look at the motor oil, not much happening there. Not much happening on the olive oil. oh, but look at this. My water is definitely now going from being a solid to a liquid.
Yep.
And my nitrogen and my oxygen have already gone. Right? They've already evaporated. They've already turned into a gas. Yeah. So now, if we look at the formulas, here is relatively small molecules, oxygen and nitrogen, water, gasoline, C8. If we look at C14, C18, not much happening yet. And if we look at the sodium chloride or the baking powder or the baking soda, not much is happening.
Mm-hmm.
Okay, ask a question.
You mentioned that the smaller formula you pointed out smaller formulas, and they seemed to be melting or boiling pretty quickly, like the water and the oxygen and nitrogen, right?
Yes.
But then we have NaCl, and we look at the formula, there's only sodium and chlorine in it. But if we look at the solid, it isn't melting yet.
Right. So that tells us that there must be some other type of intermolecular force at play with the sodium chloride, right? There's obviously got some sort of strong forces. I mean, we can see the gasoline boiling like crazy. We've seen the water melt, and nothing is happening in the sodium chloride. So it obviously has some sort of really strong intermolecular force holding it together.
Okay.
A lot of this our students know already. They just may not have been forced to articulate it or to think about it.
Yeah, that's true. Oh, I have another question.
Okay, fire away.
If we look at the formulas for both of the sugars, they seem to be exactly the same. Did you have any reason to include both of them then?
Well, I know that in my head, brown sugar always melts a little more quickly than white sugar does. And so I assume that while they're basically the same compound, that the brown sugar still has some, what we might call impurities. Some people might call it like the special characteristics of brown sugar. And so I think that's why that's why I put them both in there, because I thought we might see a difference of melting.
Okay.
But I don't
progress yet with any of the other substances?
Well, I'm still a little nervous about that gasoline, but I'm not seeing anything happen on the olive oil yet, or on the motor oil. The gasoline is almost all boiled off, so at one level I'll be glad when it's gone.